In this video, I'm going to talk about the traveling salesman problem and why it's so hard for a computer to solve. But before I start talking about the problem itself, I want to talk about two things that are really important. Number one, permutations, and two, factorial growth. Okay, so flipping a coin. Every time you flip a coin, it could either land on heads or tails. But what happens if you want to know all the possible outcomes of flipping 3 coins? So you flip a coin 3 times, how many different possible outcomes are there? Well, there's heads, 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 tails. So there's 8. I want you to notice that in each column, there's 2 columns here, and in each column is made up of 3 separate columns. So if you look at each column and look at the last 2 columns in each column, you'll notice that the patterns on both sides are the exact same. So you could see that on both sides, the last 2 columns are heads, 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 tails, tails, heads, and tails, tails. The reason why this is because if you flip the coin 2 times, there would be only 4 possible outcomes. Those 4 possible outcomes are what you see on the last 2 columns, the heads, 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 tails, tails, heads, and tails, tails. That's the 4 possible outcomes in flipping a coin 2 times. So when you flip it 3 times, there's all those 4 outcomes, and there's 4 of those outcomes, one for when head precedes them, and one for when tails precedes them. Each time you add an extra flip to a coin, there's going to be the same amount that was there the time before it, times 2. So it's just going to keep doubling over and over again. You could easily calculate the amount of permutations in a number of coin flips by raising 2 to the nth power, where n is the number of flips. If you're flipping a coin 10 times, you could say 2 to the power of 10, and that'll give you the amount of different permutations you could expect from 10 separate coin flips. This is called exponential growth, when something keeps doubling over and over and over again. So it starts off as 2, then 4, then 8, 16, 32, 64, 128. It just keeps getting bigger and bigger and bigger. Now, it could be really counterintuitive to imagine how big something gets when it's increasing its value exponentially. For example, let's say you have a piece of paper that's as thin as a paper that would be on a newspaper. So a really thin piece of paper. And let's say you have a really, really big sheet of paper, just a huge sheet of paper. You fold it 100 times. So you fold the piece of paper in half, and then you fold it again, and you keep folding it 100 times. Every time you fold that piece of paper, the width of the paper is essentially doubling. It's getting twice as thick every time you fold it. So how thick would the piece of paper be when you fold it 100 times? Lots of people think, well, it'll be like 4 feet thick. Or it'll be, as thick as my house. Or it might be as thick as the Empire State Building. The truth is that I don't know exactly how thick it would be, but it would be more measured in light years than it would be in feet. It's probably bigger than the galaxy. It's just huge. And it's a simple mathematical formula. You could do that. Just start at a very small amount, and you double it 100 times. The exponential growth of that value is so that it just gets bigger and bigger and bigger. You can kind of understand how exponential growth can just get out of hand really quickly. And it's important to understand this sort of how things grow as n grows, as the amount of folds grow, or as the amount of flips grow in a coin. It's really important for the traveling salesman problem to understand how the values just get out of hand as n increases. It's really important. So you flip the coin 50 times, and you determine that there is this amount of different outcomes. I don't know what that is. It might be 112 trillion. I don't know. I didn't really check. In any case, in that amount of permutations, you're flipping the coin 50 times, right? And in one of those permutations is one of the outcomes where the coin lands on heads every single time. Okay, let's quickly talk about dice. A regular 6-faced dice has 6 possible outcomes for every roll. You can easily calculate the amount of permutations in a given number of rolls by raising 6 to the nth power, where n is the amount of times you're rolling the dice. 6 dice rolls yields 46,000 different possible outcomes, and 12 rolls yields 2.1 and change billion different possible outcomes. And 100 dice rolls yields that amount of different outcomes. That's a 78-digit number. Now to the second thing, factorials. So you have 5 colors, right? You can see it right here. There's 5 different colors. So I want to ask you, how many ways can you rearrange them? So, okay, it's simple enough. So you could swap the cyan and pink. Okay, so that's one different way to organize them. You could swap the purple and orange. And I'm not going to go through on these slides all the different ways that you could rearrange them because there's a lot. There is 120 different ways to arrange these, and you can calculate it by doing 5 factorial, which is 5 times 4 times 3 times 2 times 1 equals 120. That's what factorial is. It's basically like if you were calculating 15 factorial, it would be 15 times 14 times 13 times 12, yada yada yada, times 3 times 2 times 1. So with that, let's say you were trying to find out how many different ways you could rearrange the 26 character English alphabet. So you already know how to calculate this. It's just factorial. So 26 times 25, yada yada yada, times 2 times 1. It equals this long number, 403, 291, 461, 126. Just a long number. That's a lot of different possible ways you could rearrange the alphabet. So I already mentioned earlier in the video that when you're flipping a coin, it sort of grows exponentially the amount of different outcomes. And when you're rolling a dice, it's even worse. It gets instead of just doubling every time, it's the values being multiplied by 6 every time. So it'd be 6 to the power of n. That's pretty explosive. Like the growth of it grows really quickly. So calculating the amount of different permutations in, 5 coin flips isn't that much. But once you get to like 25 coin flips, you've only increased it by 20, but the amount of possible different outcomes is just so much bigger than it was at 5. Well, factorials is even worse. It's really, really explosive. Like the amount of ways you could rearrange things when the input size of n gets bigger. This is what's really important for the traveling salesman problem. Because the traveling salesman problem doesn't get bigger exponentially, it gets bigger factorially. Let's talk about a 52 card deck of playing cards. So this is, the cards you play poker with. There's 52 cards. How many ways can you rearrange a deck of cards? I don't know if you knew this, but every time you shuffle a deck of cards, it is more likely than not that a deck of cards has never been arranged in that particular way. Every time you shuffle a deck of cards, the order of cards is more likely than not completely unique. And you could know that just by calculating 52 factorial and seeing how big that number is. 52 factorial is so big that it sort of doesn't look that big, but it is. I'm going to try to help you understand just how big that number is. Because this number, you could write it down. You don't really need scientific notation for it. It's not like those, it's not like a Googleplex that has, like a million zeros in it or something, This is a 91 digit number. So that's a lot. That's 91 digits. It's a really big number. I'm going to try to help you imagine how big that number is. So you set a timer counting down that amount of seconds. To kill the time, you stand on the equator and take one step forward every billion years. Every time you complete a lap around the planet, take one drop of water out of the Pacific Ocean. When the Pacific Ocean is empty, lay down one sheet of paper, refill the ocean, and keep carrying on. When the sheets of paper reach the sun, the timer has run out. I'm just kidding, no it hasn't. You have to repeat this process 1,000 times. And that would kill 1/3 of the time. So we're not done yet. You still have a long time to wait. So you're tired of walking around the planet, and you're tired of laying down sheets of paper, so you do something else to kill the time. You shuffle a deck of cards and deal yourself 5 cards every billion years. And each time you get a royal flush, you buy a lottery ticket. And a royal flush is just a 10, jack, queen, king, ace, all of the same suit. So all spades, all hearts, whatever, it doesn't matter. So each time you get a royal flush, you buy a lottery ticket. Every time you win the lottery, throw a grain of sand into the Grand Canyon. When the Grand Canyon is full, take a 1-ounce rock off Mount Everest and empty the Grand Canyon of sand. Then, when Mount Everest is leveled, check the timer. You'll see that it's barely nudged. You would have to repeat this process 256 times until the timer has fully run out. Now realize that that's only using 52 different objects, 52 playing cards. Not 52,000, nor 5,200, just 52. So imagine if somebody gave you like a deck of 400 cards, and you wanted to know how many different ways that 400 card deck could be rearranged. It'd be insane. There's just, even at 52, now here's the thing though, 52 is really big, but 400 isn't like 8 times bigger than 52. 50 times 8 is just 400. I'm leaving off the 2, I'm just rounding it a little bit. The point is that 400 different cards, it wouldn't be like waiting 8 times the amount of time that you had to wait for 52 factorial seconds. It would be so much bigger. Like, you just can't even imagine how big that number would be. Or can you imagine how many permutations exist in rearranging 5,200 objects? So now we're ready for the traveling salesman problem. I've kind of already touched upon why this problem is so hard to solve. That's because as the size of n increases, the amount of different permutations for the problem increases factorially. So let's see what the actual problem looks like. You see these little points on a map here. There's 4 different destinations. So a traveling salesman wants to calculate the shortest possible path to reach all of his destinations. And each destination has a time to travel to every other destination. In this example here, how would he, from starting at point A, how can the salesman reach B, C, and D in the shortest amount of time? Well, if he goes from BC to D, that's 22 hours. If he goes from DC to B, that's 29 hours. If he goes from C, B to D, that's also 29 hours. And if he goes from D, B to C, that's 33 hours. And if he goes from B, D to C, that's 21 hours. So that would be the shortest. And that's not all possible permutations. I left some out, but point is that the only way to be sure that you have the shortest possible route is to calculate every possible route. There's no like magical way to split them in half and then calculate that. You know, like for sorting algorithms, you could split the pile in half and then keep splitting them in half and sort of like, you know, you could divide and conquer it. You can't do that for a traveling salesman problem. So let's change some of these values. So this is an updated map here. It looks a little bit different. I changed some of the values. What do you think the shortest way for the traveling salesman to reach all possible destinations is this time? Go ahead and try to figure it out. Pause the video if you need to and see what you get and then see if it's the same as mine. So the fastest way here is to go to C, and then come back to A, then go to B, and then go to D. That would take 16 hours. So it's really important to also notice that the fastest possible way might include backtracking. So you don't just have to, you're not burning bridges here. It might be a logical thing to do to backtrack to a place where you've already been, if that's the fastest way to go, because that's all you really care about. You don't care about, oh, I've already been there, I don't want to go there again. You're just worried about saving time, saving money. That's all you care about. You just want to get there the fastest. So let's increase the amount of destinations. So a map like this has a bunch of destinations. I'm not even sure how many there are, I didn't count, but there's a lot there. I don't know, maybe like 15, 20, I'm not sure. Anyways, I'm not going to fill out every different possible permutation here, because there's probably a lot, but you could already imagine that getting a computer to calculate this would take a very long time. This isn't even the worst case scenario. Like, what if you had 100 points on a map? Well, you've already seen how big 52 factorial is. It's too big. There's too many possibilities there. A computer can't do that. It would take too long. So that's kind of the reason why this problem's so hard. There's no way to hack it. There's no simple way to break it down. You just have to brute force it. You have to calculate every single possible different way, every possible path that you could think of. Even if it might not make that much sense. Like you might think, well, why am I going to go from point A to point Z and then go back to point B? It might not be a good idea, and you might be able to look at, as a human, you could look at it and say, I could see that that's going to take a lot longer, but a computer doesn't really think like that. A computer is just following simple instructions. So you have to give an algorithm that's going to check and give you the best answer for any possible map. What if you gave it a map where going from A to Z and then back to B? What if that was the best possible way? You would want the computer to let you know about that. You wouldn't just want the computer to say, hey man, I'm going to go like A, B, C, D, E, F. I'm just going to follow it like that. Because then, what if that's not the right way? Computers don't do magic. They just follow simple, logical instructions. The reason the traveling salesman problem is so difficult for a computer to solve is because as the number of destinations grow, the amount of possible routes grows factorially. And the only way to be sure that you've calculated the shortest route is to calculate all possible routes, which can take a very, very long time. Thank you for watching. I'll see you next time.